Okay, Assalamualaikum and good day to you. Okay, today we will continue our lecture on energy of the gas. Okay, previously we have learned on the relationship between pressure and volume and temperature. We have learned a few gas laws. Okay, and then we have ideal gas law. Okay, today we are going to go deeper into this topic, which is uh, energy of the gas. Okay, so before we understand or we discuss about energy of the gas, so first we have to go through few assumptions that we have to make in order to understand this topic. Okay, the first assumption is assumption of the kinetic molecular theory. So this is assumption we need to make in order for us to understand the energy of the gas. So the first assumption is the volume occupied by individual gas particles of a gas is negligible compared to volume of the gas itself. So what does it mean? It means that the size of the gas particle, individual gas particle, one gas particle is very small compared to the volume of the whole gas. Okay, so individual size of the gas particle is very small, so small that it can be negligible. Okay, diabaikan. Okay, compared to the whole volume of the gas. Okay, that's the first one. Second one is, the second assumption is the particles of an ideal gas exert no attractive forces on each other or on their surroundings. Okay, this means that in between the particles there is no attractive force. Okay, so no attractive force among them. Okay, second one, the third one is gas particles are in constant state of random motion and move in straight lines until they collide with another body. Okay, this is straightforward lah. Okay, number 4, the collision exhibited by gas particle are completely elastic. Okay, so the total kinetic energy is conserved. Okay, the last one is the average kinetic energy of a gas molecule is directly proportional to absolute temperature only. Okay, so these are all the 5 assumptions we have to make, okay, before we discuss. Okay, okay, now since we already make or understand the assumption, okay, let's start to calculate energy of the gas. Okay, to calculate the whole energy of the gas or the gas in a container, so let's first we focus on one atom or gas particle only at the moment. So in order to understand the energy of the whole gas, let's focus on one gas particle or atom only, okay, or one molecule only. Okay, so we are going to calculate energy for this one gas particle, atom or molecule of the gas. Okay, so in order to do that, definitely we have to declare something lah. Okay, so energy of one gas particle or molecules is called average kinetic energy. Okay, so whenever you see the word average, it means it refer to energy of one gas particle or one molecule only. Okay, the word average, whenever you hear it or you read it, it means one energy for one gas particle or molecule only, average. So in order to determine the energy of the gas, okay, to determine average kinetic energy of the gas, so we have to classify the gas lah. Okay, classify it into several classes, and then we also have to know how does it move. Okay, the way it moves, we call it as a degree of freedom. Okay, later we will see that. And then since it is moving, definitely the energy is kinetic energy. Okay, So what are the classification of gas? Okay, so gas can be classified into three types. Okay, three types. Three classes. Sorry. Okay, the first class, okay, is monatomic gas. Okay, it means it only has one single atom. Monatomic. Example is helium, neon, and argon. Okay, and many more. Okay. Second one is diatomic gas. It means it has two atoms. Okay. Example is oxygen or nitrogen, hydrogen, fluorine, and so on. Okay. The third class is polyatomic gas. Okay. Means it has more than two. Okay, definitely more than one. Poly is more than two. In this case, more than two, because two is diatomic. Okay, very straightforward. So these are the example: carbon dioxide, methane, benzene, CO2. Okay. Right. So you have three classes: monatomic, diatomic, polyatomic. Okay. So of course, since the number of atoms are different from monatomic, diatomic, and polyatomic, so the way they move also different. Okay. Like monatomic, the diatomic can move in a way that monatomic cannot. Okay, polyatomic can move in a way that diatomic or monatomic gas cannot move. Okay, so uh, we will look into that. Okay, and the way it move, we call it degrees of freedom. Okay, so degrees of freedom is number of independent ways the molecule may move, rotate, or vibrate. Okay, so we give symbol F to uh, represent what the number of degree of freedom, or the number this particle can move. F, symbol F. Okay, alright. So the first type of motion, mode of motion is translational. So translational, it means the particle move in, okay, x, y, z. Okay, so it means translational simply a linear motion. Okay, and it happen for monatomic gas. Okay, monatomic gas or monatomic particle. So monatomic particle, monatomic gas has translational motion. So we have x in x direction, y and z direction. So we have three degrees of freedom. F equal to 3. The number of degree of freedom is 3. Okay, x, y, z. Okay, now for another mode of motion, type of motion, we call rotational. Okay, this happen for diatomic particle, diatomic gas. Okay, okay, it still have x, y, and z motion, but it has extra rotational motion here and here. So now we have 5. For diatomic gas, we have 5 degree of freedom. So the number of degree of freedom is 3 plus 2. 3 is translational plus 2 rotational. Okay, this is for diatomic gas. Okay, for diatomic, okay, if the temperature is very high, for example more than 1000, it can also vibrate. Okay, it can also vibrate. So it has extra motion, extra way of moving. Okay, for diatomic at higher temperature, let's say more than 1000, it can vibrate. So, or if polyatomic, it also can vibrate. So it will have 3 from translational, 2 for rotational, plus 1 for vibrational. So diatomic at high temperature or polyatomic will have 6. Okay, in total 6 degrees of freedom. So it can move in 6 ways. Okay, we can say that it can move in 6 ways. Okay, for diatomic at high temperature and polyatomic gas. Okay, so make sure you understand the differences. Okay. Alright, these are just notes you can go through, okay? But make sure you understand this part. All molecules have at least 3 degrees of freedom because it is for translational motion. So, all whether monatomic, diatomic or polyatomic will have translational motion, okay? At low temperature, there can be no rotational motion. For diatomic, okay, vibrational motion can only present at very high temperature. Okay. Okay, now we move to another subtopic, which named theorem of equipartition of energy. Okay. Theorem of equipartition of energy states that when a certain amount of energy is supplied to a system, energy is shared equally amongst all degree of freedom. Okay, so imagine, let's say the gas is supplied by 500 joule, let's say 500 joule, and it has 5 degree of freedom. So it means every degree of freedom will share equally. So 500 for 5 degree of freedom, it means you have for 1 degree of freedom is 100. Okay, that is what it means by energy is shared equally. Yeah, alright. So each degree of freedom, or that is just an example. Okay, so each degree of freedom will have half kT of energy. Okay, let's look the picture to make understanding easier. Okay, so for monatomic we have 3, okay, which is translational motion. Okay, 3 degree of freedom. So each degree of freedom will have half here, and then half here, x direction, half here. So all is shared by half. So in total, it will have 3 times half kT. Okay. So the average kinetic energy for monatomic is 3/2 kT. Okay, 3 times half. Okay. For diatomic gas molecule, okay, it has 3 translational and 2 rotational. So in total it has 5. This it means 5 times half. Okay, 3 here linear plus 2 for rotational. Okay, sorry, this one. Okay, this one. So 3 plus 2, 5. So the average kinetic energy of this gas is 5 times half kT. Okay, remember average means it is one molecule, not the whole gas of energy. Yeah, it is energy for kinetic energy for one gas molecule only. So how to find it? It is 5 times half kT. K is our Boltzmann constant, T is our temperature. Okay, don't worry, we will look at the example. Okay, so this is a summary. Yeah? Okay, alright. For helium, for example, we know helium is monatomic. It has translational motion. The degree of freedom is 3. So the average kinetic energy per molecule is 3/2 times 3/2 kT. Yeah? 3 times half kT. For hydrogen, it is diatomic. Okay, it has 5 degree of freedom, 3 from translational, 2 from rotational. So it is 5 times half kT, and so on. Water, it has 6, and so on. Okay, remember this kinetic energy for one molecule or gas particle only, not total. Okay, remember whenever you hear the word average or read about average kinetic energy, the word average refer to one molecule or gas particle only. Okay, now let's look at the example. Okay, a nitrogen gas is kept in a container at this temperature. Nitrogen is diatomic. Calculate the average translational kinetic energy, average rotational kinetic energy, average kinetic energy, and average kinetic energy for 5 mole. Okay, so it refers as average, meaning one molecule only. We only would like to calculate energy for one molecule only. So first one is average translational, meaning it only, although it is diatomic, we know we have 5 degrees of freedom, but we want only, for question number 1, we only want to know the average kinetic energy for translational modes only. So we only take 3/2 because it is translational only. Okay, so straight away plug in the formula and you will get this. Okay, please go and refer back your notes lah. Okay, so average rotational kinetic energy, only rotational, only based on rotational motion. So rotate, it has 2 degree of freedom, so 2/2, 2 times half kT. Okay, we will get this. Okay, average kinetic energy, meaning it has, this is diatomic, we have to consider transitional and rotational, so it should be 5 kT. So we'll get this answer. Okay, that one is for as I said, average kinetic energy is for one molecule or gas particle only. But what if they give us 5 mole? Okay, so how to find average kinetic energy for 5 mole? So you can either find out how many gas particles are in 5 mole, and then we times the average kinetic energy. Cool. Okay, so I will introduce this formula in the next few slides. Okay, so in this case, okay, let me explain first. They want energy for 5 mole. Okay, so based on this average kinetic energy that we calculate, we have to times number of molecules for 5 moles, or use this formula. Okay, okay, since we already know how to calculate energy or kinetic energy for one gas molecule or one gas particle, so what we have to do if you want to calculate energy for the whole gas, so simple. The idea is, since we know energy of one, in order to know all the energy of the gas, we simply times the number of molecule of the gas. Okay, let's say, okay, energy for 1 is 1 joule. Let's imagine lah. And inside we have 20 billion of molecule. So it means we take 1 joule times 20 billion. So we'll get 20 billion joule. Okay, which is, the number is too high lah. Okay, but that is the idea. So simply take 1 times all the number of molecule or particle inside. Okay, so we know this formula. Okay, this is for one gas particle or molecule. So in order to get the whole total kinetic energy, we simply multiply average kinetic energy with number of gas. Okay, so now we no longer use the word average, we use the word total kinetic energy. Okay, so it refers to energy of the whole gas. Okay, this is the formula. Okay, we simply times n, number of molecule. Okay, we take this formula on the left, we times n, so we get energy for the whole gas. Or if you are given number of mole, okay, we can use this formula. Careful, this one is N, big N, KT. This one is N, small n, RT. Okay, don't get confused. Okay, kinetic energy depends only on temperature, not mass or anything. It only depends on temperature only. So example, please go through this example. It's very easy. Average translational kinetic energy. Okay, because it only one translational, so it is 3. Okay, so and it is also average, meaning one gas particle only. So you get this answer. And then for total kinetic energy, it means we have to times this figure with time with the number of molecule. Okay, or we can use this formula. Okay, because we are given with number of mole, apply this formula. So either one, this one or this one. Okay, this, sorry, I forget to put 8.31 here. Okay, so you will get this figure. Okay, this is total kinetic energy for the whole gas. Okay, please go through in your. Now we learn about average kinetic energy and total kinetic energy. Now we have another terminology, which is internal energy. Okay, so in order to understand internal energy of a gas, we have to know what is gas actually. A gas is a store of energy. Okay, because it has energy. So we say it is a store of energy. So for real gas, actually internal energy equal to total kinetic energy plus potential. Okay, but remember we assume that between particles there is no attractive force. So for ideal gas, there should be no potential energy. Okay, for ideal gas. So for ideal gas, internal energy equal to total kinetic energy. So how to calculate? Simple. If we find the value of total kinetic energy, that means that is the internal energy. Okay, so same calculation but different name. Okay, same thing. So meaning it is same thing, because this is for ideal gas. For ideal gas. So if I ask what is internal energy, it is actually total kinetic energy, energy of the whole gas. Okay, so you can apply this formula or this formula, either one. You please go through the example. Go by your own. Try to go the example on your own. Okay, inshallah you can do it because it's very easy, very clear. I have shown everything, all the steps. Okay. Okay, for average kinetic energy. Okay, for translational kinetic energy again, hydrogen is diatomic, but the first Roman it only asks translational, so we only use 3, only translational. And then average kinetic energy, definitely we have to consider all the degree of freedom, which is in this case diatomic 5. Okay, and then internal energy, simply a total kinetic energy. Okay, you will get this answer. So sometimes, okay, if you use this formula or this formula, definitely the answer could be slightly off, because they are using different constant. Okay, now since we know energy of the gas, what is the speed of the gas? Okay, what is the speed? We know it has some kinetic energy. Definitely, it is moving. So what is the speed? Okay, so we are familiar with this formula, half mv square from school. So we know that this v refer to linear motion. Okay, linear motion, moving in a straight line, linear. It's not rotational, it must be in linear motion. Okay, so let's visualize a gas. Okay, let's imagine this gas particle is moving this way. Okay, so mathematically we can write like this, right? Using our theorem Pythagoras. Okay, this speed equal to this speed plus this speed square, like this. Or if it is 3D, it is like this, x, y, z. Okay, So, okay, this mode of motion is what? This is translational because it's linear, not rotational vibrational. So, to find what is root mean square, okay, we can write like this, okay. This is average kinetic energy for one gas particle or molecule. We can equate to our glamour formula, half mv square, okay. Now V is average, V square, average. We can rearrange, okay, and we get these two terms. So we get this formula and this formula, okay. Alright, here V average, okay, here you rearrange and square, okay. This we give them new name, okay, which is RMS, meaning root mean square. So V square average, if we square root it, we give it new name. So the name is root mean square speed, okay. What is root mean square speed? It is molecule at which all molecules have same total kinetic energy, okay. So you either use this formula to find VRMS or this formula, okay. This one is just I want to show how the formula is derived, okay. And this V is only meaning linear only, okay. That's why this will not become other number. It will stick to 3, number 3, yeah, not 5. Although it is polyatomic, diatomic, it is still 3 because V only account for linear motion, okay. Example, please go through. You are given T temperature, so apply the formula, or the second one, same, you should get the same answer, okay. VRMS for diatomic and polyatomic, so definitely lah not this one, okay. Why? Because VRMS is only for linear. So for linear, only translational motion 3, yeah, not 5. So although it is diatomic or polyatomic, the formula is still the same as monatomic. So the RMS speed is square root 3 kTm or 3 rtm, okay. So summary for this topic is this, please go through, okay. So total kinetic energy and this formula should not be confused with this formula, okay. And please memorize this formula, okay. Very simple one, okay. This is distribution of molecular gases speed, okay. We only learn how to calculate root mean square speed, okay. The other no, but it's good to know what are they, okay. You don't have to calculate most probable speed and average speed, but only root mean square speed, okay. But it's good to know that, okay, this graph show x, y axis is number of molecule, okay. X axis is the speed of the molecule, okay. If majority of the gas, the speed are known as most probable speed. So if we can measure speed of all gases, all particles in the gas, you will somehow get some value, let's say 10 meter per second, let's say. So most of the gas particle will have that value, and that value is we call most probable, okay. Let's say 50% of the gas particle or majority of the gas particle will have that speed, okay. We call that speed as most probable, okay. And then maybe out of that 50% has most probable speed, maybe let's say maybe 35, Okay, 35 will have an average speed of 15. Okay, 35. And then the lowest number of gas particle, maybe 20%, the remaining 20% or 15 will have a speed that known as root mean square speed, the one that we calculate. Okay, so you can refer to this graph. It is quite self-explanatory. Okay, and please read this as well. This is just good general knowledge. I will not ask you to draw or anything, but I want you to understand this statement. What is root mean square speed? It is the speed at which all molecules have the same total kinetic energy. This is just example. Mean speed also known as average speed. Average speed versus root mean square speed. Okay, how to calculate? Okay, see here it has negative, meaning in negative direction. The rest are positive. Okay, for mean speed or average, okay, the negative direction will give an impact. So see here, the total is 3 meter per second. But if we square and then square root, it will give us different speed. Okay, so that's how the calculation and direction give impact to the value of speed. Okay, that's it. Okay, this is just notes about how kinetic theory of gases is derived. We will not go into it. Okay, but maybe I will put the notes in the spectrum lah. Okay.